Welcome to my class on Laplace transform. In today's class we are going to discuss about inverse Laplace transform. Now in the previous class we have discussed the definition of Laplace transform, its existence criteria. We have discussed three very important properties, one being the linearity property, then the change of scale property, and the first shifting theorem. Now today I am going to discuss what is inverse Laplace transform, the concept of inverse Laplace transform, followed by various types of examples where you are required to find out the inverse Laplace transform. Now the concept of inverse Laplace transform is something like this. If Laplace transform of ft is known to be equal to f bar s, then the function ft, that is the function of time, is actually called the inverse Laplace transform of the function of s, and is normally denoted by L inverse f bar s is equal to ft. So if L of ft is defined to be f bar s, then the function of time, that is ft, is said to be the inverse Laplace transform of f bar s. This is the way we define the inverse Laplace transform of a function. The inverse Laplace transform given below at once form the results of Laplace transform given earlier. Yes, the Laplace transform that we have done in our first lecture, okay, that is the Laplace transform of some standard functions that we did, 7 functions we did. So easily we can write the inverse Laplace transform of those functions, because if Laplace transform of function is known, its inverse can easily be obtained, right? So we start writing the results one by one, like L inverse of 1 by s is equal to 1, because we proved earlier that L of 1 was 1 by s. So 1 is the inverse Laplace transform of 1 by s. Similarly, e to the power at is the inverse Laplace transform of 1 by s minus a. T to the power n by n factorial is the inverse Laplace transform of 1 by s to the power n plus 1, where we are assuming that n is a positive integer. Similarly, e to the power at into t to the power n by n factorial is the inverse Laplace transform of 1 by s minus a to the power n plus 1. Now here if you look carefully, we have also used the first shifting theorem in this definition, because if you multiply the function by e to the power at, there is a shift of the origin at a, so that is s minus a it becomes. So that's why the inverse Laplace transform of 1 by s of 1 by s minus a to the power n plus 1 will be e to the power at into t to the power n by n factorial. Similarly, 1 by a sin at is the inverse Laplace transform of 1 by a square plus a square. Because a is a constant, so we can bring it down. Inverse Laplace transform cos at is the inverse Laplace transform of s by a square plus a square. 1 by a sin hyperbolic at is the inverse Laplace transform of 1 by a square minus a square. And lastly, cos hyperbolic at is the inverse Laplace transform of s by a square minus a square. Similarly, if we apply the shifting properties on these functions, accordingly the point will get shifted. So like here in the case of sin bt, if you multiply it by e to the power at, okay, divided by b, so this is actually the inverse Laplace transform of 1 by s minus a whole square plus b square, because we know the Laplace transform of e to the power at into sin bt is b by s minus a whole square plus b square, which we did in the previous class, in the shifting theorem class. Okay, then similarly if you multiply cos bt by e to the power at, so there will be a shift, and that is showing here, that is e to the power at into cos bt is the inverse Laplace transform of s minus a by s minus a whole square plus b square. So whenever you are defining the Laplace transform of function of t, which is normally f bar s, so the inverse Laplace transform of f bar s is actually the function of t, whose Laplace transform is f bar s. So that is always defined. So that is the way we define the inverse Laplace transform of a function. So having defined this inverse Laplace transform, now we come to some problems. We'll do a bit of problems today, because there are various types of problems that you might encounter in finding out the inverse Laplace transform. That is very, very important for the study of Laplace transform, how to find the inverse of a function of s. Like if you consider this function, find the inverse Laplace transform of 4s plus 15 divided by 16s square minus 25. It's not always that the function will be of those 7 standard forms, but what we'll try to do is that in all the problems, our main objective will be to convert this function of s into the known standard functions of S. Those 7 standard results we know. So we will try to convert this function of S into that known standard function of S, so that we can use those 7 results and easily get the inverse Laplace transform of those functions. So how we convert this function into that function, that is very important. That is the main thing here. Now suppose you are given this function 4s plus 15 divided by 16s square minus 25. Now how we convert this function into those known forms? You see, we take 16 common from the denominator. So if we take 16 common, we can write this as s square minus 25 by 16, which we can write in every next step s square minus 5 by 4 whole square, right? So we are getting s square minus a square form. And now if you divide term by term, you get, so 4s by 16 into s square minus 5 by 4 square. So 4 and the 16 cancel, makes it 4 in denominator. So eventually get s by 4 into s square plus s square minus 5 by 4 whole square. And the other one you get 15 by 16 into 1 by s square minus 5 by 4 whole square, right? Now if you look at this function very carefully, which we have modified, it is coming in the known forms, isn't it not? You see this one, s by s square minus a square is a known standard form. Like here 1 by s square minus a square is also a known form. So these are hyperbolic functions. The first one being cos hyperbolic, second one being sine hyperbolic, isn't it? So once they are known, now you are in a position to find the inverse Laplace transform. So now I will take the inverse Laplace transform of this function both sides. I'm going to apply the linearity property and I'll arrive at the result from the known standard result. That means if I take the inverse Laplace transform on both sides, so I get L inverse of 4s plus 15 divided by 16s square minus 25, which comes out to be equal to 1 by 4 into L inverse of s by s square minus 5 by 4 whole square plus 15 by 16 into L inverse of 1 by s square minus 5 by 4 whole square. As simple as that, because constant will go outside by the linearity property, and hence you are left with L inverse of s by s square minus s square, which is cos hyperbolic 5 by 4t. It's a very standard form, standard result. So we can directly put it over here. So we are doing that. And in the second term, you see it is L inverse of 1 by s square minus 5 by 4 whole square. Again, it's a known form. L inverse of 1 by s square minus s square, which is sine hyperbolic at t. So therefore, this will be sine hyperbolic 5 by 4t multiplied by 1 by a, that is 1 by, in a in this case is 5 by 4. So 1 by 5 by 4 or 4 by 5, whatever we write. So now on further simplification, you will get the answer of this question. So you get 1 by 4 cos hyperbolic 5 by 4t, and we get 3 by 4, some factors cancel, 3 by 4 sine hyperbolic 5 by 4t, which is the final answer of this particular question. So you see how we modify the function into the known form. That is the most important thing in inverse Laplace transform. In the example that is going to follow, you see that all the problems are of different types and how we are converting these functions into ultimately those 7 known forms, so that we can take the inverse Laplace transform and get the answer directly out of it. Like in this problem, very next problem, find the inverse Laplace transform of this function s plus 1 divided by s square plus s plus 1. Now how we get it? Now if you look at this function very carefully, you can bring this function into the known form. Now how we can do that? Now you look in the denominator, is s square plus s plus 1. So there is no twice s term, but you can bring a twice s term in the form of, if you consider s plus half whole square. If you consider s plus half whole square, you get these two terms first, s square plus s, and you are left with the constant term 1 by 4. But the constant is 1 here, so you just subtract 1 minus 1 by 4, that means 3 by 4 has to be added. So that makes it 1. So therefore, your denominator s square plus s plus 1 can be represented as s plus half whole square plus 3 by 4. Now why I am writing that? Very simple, again in the form of s square plus a square form. Okay, that plus half will be taken care of by the shifting theorem, right? Now when you are making s plus half in the denominator, you have to make it s plus half in the numerator. Otherwise, shifting theorem cannot be applied. It's not that shifting takes place here, doesn't take place here. That's wrong mathematically. So I need to modify the numerator also. So I write s plus, I break one as half plus half. I club s and half together as a single term and keep the other one aside. So it's plus half. And then I simply divide term by term like I did in the previous case. So it becomes s plus half divided by s plus half whole square plus root 3 by 2 whole square. And you are left with plus half, the other term, 1 by s plus half whole square plus root 3 by 2 whole square, because I am writing in the square form. So it's root 3 by 2 whole square. And now you see you are now in a position to take the inverse Laplace transform of this function. Earlier you were not, because this is totally confused to you, because you are not able to say what will be exactly the inverse Laplace transform of this function. But now you will be able to say it. So that's the main thing in this problem. You have to convert this function into the known forms of those inverse Laplace transform results. So now if you take the inverse Laplace transform on both sides, so you apply the linearity property, so it will be L inverse of this plus half into L inverse of this, and that's what I would write here next step. Yes, you see, L inverse of this plus half into L inverse of this. Now what is L inverse of this part? S plus half divided by s plus half whole square plus root 3 by 2 whole square. So it is of the form s by s square plus a square form. That means it is cos 80 form. Yes, cos 80, but one thing to be kept in mind, because it is s plus half, which means there is a shift of origin has taken place. So you have to, don't forget to multiply cos function with e to the power minus half t. That means e to the power minus t by 2. Because it is plus here, so there will be minus. I told you the theorem, the first shifting theorem in the previous lecture. So I think you have understood. So it's e to the power minus t by 2 into cos root 3 by 2t, because your a is root 3 by 2, right? Similarly, you will get the second term. The second term is L inverse of 1 by s square plus s square, which is sine. So again here you see there is a shift has taken place, s plus half whole square. So you have to keep that in mind, which means you have to multiply sine with e to the power minus t by 2. You see, I have done that here. And don't forget, L inverse of 1 by s square plus s square is 1 by a sine 80. Then 1 by a must be there. A being root 3 by 2, so it's 1 by root 3 by 2 or 2 by root 3, same thing, multiplied by sine root 3 by 2t. So now on a bit of simplification, if you like, you can take 1 by root 3 into the power minus t by 2 common. And if you do that, you will get the answer into this simplified form is root 3 cos root 3 by 2t plus sine root 3 by 2t. So that's the way we solve the second problem. You see, it's a bit different from the first problem. In the first problem, we are able to get s square minus s square directly. But here, we have to modify this a little bit, okay, by adding some terms in between. Now coming to the third problem of today's discussion, it is find the inverse Laplace transform of 2s square minus 1 divided by s square plus 1 into s square plus 4. Now this function, see, already the factors are in the form s square plus 2 square form. They're already in there, but they are in the product form. We need to separate these two in two different terms, and that can only be done using partial fractions. So partial fractions play a very important role in determining the inverse Laplace transform. So I think all of you know about partial fractions. You have done a lot of partial fractions in your plus 2 level. So I'll be using it over here in this problem here. But before I use this split this fraction partially, I make it simple. How I can make it simple? Because since we have s square terms all over here, s square. So one thing that can be done is that the powers of s are all same. I put s square as p. If I put s square as p, things become pretty much easy for me and nothing else. So this becomes 2p minus 1. You see, you put s square equal to p over there. You get 2p minus 1 divided by p plus 1 into p plus 4. So now it becomes much easier to split it partially. So as per the rules of partial fraction, when we have non-repeated linear factors, so we can write this as some constant a divided by p plus 1 plus some constant b divided by p plus 4. Now we have to get the values of a and b. How we get it? Very simple. We take the LCM here and cancel these terms in denominator, and we get 2b minus 1 equal to a into p plus 4 plus b into p plus 1. So it's a mathematical identity. So you can put any values of p to get the values of a and b. Of course, I will be trying to eliminate b and get value of a first, for which I put b equal to minus 1. You see, if I put p equal to minus 1, b is eliminated and a is immediately obtained. So I put p equal to minus 1, this becomes minus 3. Minus 2 minus 1 is minus 3, and this becomes 4 minus 1 is 3, so 3a. So a becomes minus 1. So minus 3 equal to 3a. So a is actually minus 1. That's what we have written. And then we need to get the value of b. So we have to eliminate a, and to eliminate a we make this 0. That means we put p equal to minus 4, and the moment you put p equal to minus 4, you get the value of b to be equal to 3. So the constants are obtained. Once the constants are obtained, they are put back into the fraction that we have wrote earlier. I mean the partial fraction that we wrote earlier, and we'll get something like this. So we are getting 2s square minus 1 divided by s square plus 1 into s square plus 4 turns out to be minus 1 by s square plus 1 plus 3 by s square plus 4. So we have split the fraction partially. Here in this case we don't have to modify the denominator because the denominator is already in that form. Only thing was that we need to get them separate. Okay, then we will get the known forms, and hence we will be able to find out the Laplace inverse Laplace transform of this function. Unless we get the known 7 results, it becomes difficult to find out the inverse. Now we take the inverse Laplace transform on both sides because we are now in a position to do that. So we take the inverse Laplace transform on both sides, and let's see what we get. So on taking inverse Laplace transform on both sides, and apply the linearity property, we get minus L inverse of 1 by s square plus 1 plus 3 into L inverse of 1 by s square plus 4. Now L inverse of 1 by s square plus 1 is sin t, that is a very known form to you, and L inverse of 1 by s square plus 4 is of course sin 2t. Okay, sin 2t by 2 because it's s square plus 2 square. So 1 by a sin 80, so 1 by 2. So it's 3 by 2 is coming here. So the answer stands minus sin t plus 3 by 2 sin 2t. So it's very simple. I mean, the moment you have bring in this form, it becomes pretty simple. But the main thing is how to bring the function into that form. That is the most important thing. Coming to the fourth problem. Okay, again a bit different. Bit different in the sense that the partial fractions part is different. The rest of the thing is same. Again you see, find the inverse Laplace transform of 5s plus 3 divided by s minus 1 into s square plus 2s plus 5. So you can clearly see there is a nonlinear factor and there is a linear factor. Now we can split it partially. Degree of the denominator is 3 and the numerator is 1. So it goes by the rule of splitting the fraction partially, and so we'll go by the rule. We'll actually go by the rule and nothing else. So we'll go by the rules of splitting it partially. And if you go by the rules, as you all know the rules of partial fraction when we have a nonlinear factor, so this is the rule. That is, we write a by s minus 1 for the linear factor, and plus bs plus c, b and c, a and all three constants, divided by s square plus 2s plus 5. As simple as that. Now once it is written, we have to get the values of ABC, we take the LCM, the denominator cancel, factors cancel in the denominator. You left with 5s plus 3 on the left, right, you get a into s square plus 2s plus 5 plus bs plus c into s minus 1. So you basically get a mathematical identity involving s and the three constants, of course, ABC. So you can put any values of s to get the values of ABC, the unknowns. So what I do is that I put s equal to 1. Why I am putting s equal to 1? Because if the moment I put s equal to 1, I simultaneously eliminate b and c. So I just put s equal to 1 into the previous equation, and I get the value of a immediately. So I get the value of a equal to 1. The moment I get the value of a equal to 1, I now equate the coefficient of s square from both the sides. Now you see on the left hand side there are no coefficient of s square, which means your left hand side will be 0. And on the right hand side there is one coefficient a, and one coefficient will come from this multiplication of bs with s, that is b, which means there are only two coefficient of s square with a plus sign in between. That means it's a plus b, which means a plus b must be equal to 0. Now if a plus b is equal to 0 and a is already known to be equal to 1, so what is b? B is minus 1. So we get b. After getting b, we think of putting s equal to 0. If we put s equal to 0, we get a relation between a and c. And since a is known, c is also known. So if we put s equal to 0, we'll get a relation like 3 equal to 5a minus c. And so c will be 5a minus 3. And you put the value of a equal to minus 1, you put the value of a equal to 1 over there, and you get 5 minus 3, and ultimately you get the value of c to be equal to 2. So all the three constants ABC are obtained. Once they are obtained, they are put back into that partial fraction. So you have written this function of s, 5s plus 3. You have split it partially in the form of 1 by s minus 1 plus minus s plus 2 divided by s square plus 2s plus 5. Now I can modify this a bit. I am doing that simply because to use in the known form, because I know 1 by s minus 1 has already come in known form. It is 1 by s minus a form, but this is not. So how we do it? Very simple. We just first look at the denominator. You see s square plus twice s, which means you have to take the square of s plus 1. If you take s plus 1 whole square, you get the first two terms first, s square plus twice s. You don't worry about the constant term. The constant term can always be adjusted. So the constant term is 1, but it is 5 here. So 5 minus 1 is 4. So it will be 2 square, which is 4. So the most important thing is that you're getting s square plus a square form. And since we get s plus 1, so you have to also remodify this variable s to plus 1. And how we can do that? By adding 1 here and subtracting 3, because it will make it minus 2. Minus 3 plus 1 is minus 2, because it should be minus 2 because minus was taken outside here. So now you see s plus 1 by s plus 1 whole square plus 4, it is of the known form, and minus 3 minus plus 3 by s plus 1 whole square plus 2 square, which is again a known form. So they are all known forms, and now so you are in a position to take the inverse Laplace transform of this function and get the result out of it directly. So those results are very important. You must remember those 7 results. So we just separated it just to make it easy. Instead of taking it directly, we just write 1 by s minus 1 minus s plus 1 divided by s plus 1 whole square plus 2 square, and the other term 3 into 1 by s plus 1 whole square plus 2 square. So you take the inverse Laplace transform, because that's what we have done. No more to do, no more to reduce it further. If you taking the inverse Laplace transform on both sides, you will get L inverse of 1 by s minus 1 as per the linearity property minus L inverse of s plus 1 by s plus 1 whole square plus 2 square plus 3 into L inverse of 1 by s plus 1 whole square plus 2 square. So these are all known forms, and I hope you know what are these. The first term will be L inverse of 1 by s minus 1 is e to the power t, right? Because a is 1, so it's e to the power t. Next term will be L inverse of s plus 1 by s plus 1 whole square plus 2 square. It is the cosine function, but shifted by 1 unit. So therefore e to the power minus t will be multiplied. So that's why we did it that over here, e to the power minus t into cos 2t. And similarly here also, this is 1 by a square plus a square form. So don't forget it is 1 by a sin at, right? So a being 2 here, so it's half of sin 2t, but again a shift of origin has taken place here, s plus 1 whole square. So that has to be taken care of, which means you have to multiply sin 2t by e to the power minus t, and thereby you get the final answer. The final answer stands like this: e to the power t minus e to the power minus t into cos 2t plus 3 by 2 into e to the power minus t into sin 2t. That's the way you find out the inverse Laplace transform of this very function. Okay, see, all the problems are of different types. A lot of problems is to be practiced, because unless you are able to find out the inverse Laplace transform, then one major application of Laplace transform will be missed, that is solving ODE using Laplace transform, because there the inverse part is the most important thing. So inverse is very, very important actually. And coming to the next problem, find the inverse Laplace transform of s by s to the power 4 plus 4a to the power 4. Another very good problem to solve. Now to solve this problem, again it's not of the known forms, neither it can be brought into that form also so quickly or so by modification, but one thing can be done. It can be written as a product of two factors. This denominator I'm talking of, s to the power 4 plus 4a to the power 4. How? This is the way. We can write s to the power 4 plus 4a to the power 4 as s square plus 2a square whole square minus twice a whole square. We can do that. You see, it is actually s to the power 4 plus 4a to the power 4. Then it is a square minus b square form. So it's a plus b into a minus b. So that's what we have written. A square plus 2a square plus twice s into a square minus twice s plus 2a square. So your denominator becomes s by s to the power 4 plus 4 a to the power 4 becomes s by s square plus twice s square into s square minus twice s plus twice s square. Now it becomes easy to split this fraction partially, because you see you have in the numerator s, so you have to bring s over there, okay, but s will not come, you will get 4s. To get 4s you have to get rid of this s square and twice s square, so for which you need a minus sign. That means you write 1 by s square minus twice s plus twice s square minus 1 by s square plus twice s plus 2a square. And if you say, take the LCM and you just simplify, you see this s square and 2a square will cancel, and resulting in 4as. But you need s only, so you have to divide it by 4a. That means otherwise the function will change. So that's why 1 by 4 is coming outside over here. So 1 by 4a into this minus this. Now this becomes easy because now for next step, because when I have got s square minus twice s plus 2a square, I can write in the form of s square plus a square. For how? By shifting property, because I can write this as s minus a whole square. The moment I write s minus a whole square, I find these two terms. Now my constant term is a square, but my actual constant term was 2a square, so I have to add a square to keep it same. That means this turns out to be 1 by s minus a whole square plus a square minus 1 by, in a very similar manner, in this case it is s square s plus a whole square. If you do s plus a whole square, you get the first two terms, s square plus twice s. But the constant term is a square, but actual constant term is 2a square, so you have to add 1a square with this to keep it same. So but you get 1 by s square plus a square form. And now it is of the known form, so it is very easy problem now. So if you take the inverse Laplace transform on both sides, okay, which you are doing, you should get the result. So keep 1 by 4a outside, L inverse of, if you apply the linearity property, L inverse of 1 by s minus a whole square plus a square minus L inverse of 1 by s plus a whole square plus a square, and you get, so what is L inverse of 1 by s minus a whole square plus a square? So it's 1 by s square plus a square, L inverse of that is 1 by a sin a t. But since s minus a is there, so there is a shift of origin has taken place. That means you have to use the shifting theorem, and by using shifting theorem we will get this to be equal to 1 by a e to the power a t sin a t. And in a very similar manner, the next one is next one is also sine, but it is s plus a instead of minus a, it is s plus a. So if it is s plus a, so it is again, this function is to be multiplied by the exponential function, but with e to the power minus a t, because we have plus a here, so it is e to the power minus a t. So sin a t by a multiplied by e to the power minus a t, that will give you this. Now if you simplify this further by taking sin a t common, if you take sin a t common and you get out in denominator 4a square, you can insert 1 2 in this expression, and you get a very well known expression. You get e to the power a t minus e to the power minus a t divided by 2. Now what is that? That is nothing but sine hyperbolic a t. So you get the answer to be equal to 1 by 2a square into sine a t into sine hyperbolic a t. So that is what you have got. So that is the way we have got the inverse Laplace transform of this function. Now coming to the next question. Find the inverse Laplace transform of s cube by s to the power 4 minus a to the power 4. Now this function, if you look at this function very carefully, it's not a difficult problem, but looks like a difficult one. This can be done very easily. How we can do it? We can keep one s factor outside. We can write this s into, within third bracket, a square by s square minus a square into s square plus a square. We can break this s to the power 4 minus a to the power 4 as a square minus b square form. So if we do that, so we get this, and then we can split it partially. We need to get a square here, that means we need to get rid of a square, for which we have to just keep a plus sign in between. So we write 1 by s square minus a square plus 1 by s square plus a square. You take the LCM, you will see that a square and a square will cancel, and you will get not a square, you get 2s square. So we get 2s square, just like the previous problem. you will divide it by 2. That's why you see s by 2 is coming. So this is the speed of the fraction. And now since s was lying outside, I now just introduce this s into this term. So if you multiply this s at each term, it is becoming of a very well known form, which you all know, s by s square minus s square and s by s square plus s square. Both the forms are very well known to us. One is of course the cos hyperbolic, the other one is the cosine function. So now you are in a position to take the inverse Laplace transform. So you will take the inverse Laplace transform on both sides, and on both sides if you take and use the linearity property, half will go outside. So it will be half into L inverse of s by s square minus s square, okay, plus L inverse of s by s square plus s square. So as I told you earlier, L inverse of s by s square minus s square is nothing but cos hyperbolic at, and L inverse of s by s square plus s square is nothing but cos at. So they are known forms, so therefore I have written that, and I have got the result to be half cos hyperbolic at plus cos at. So you see, in all the problems that we have discussed so far, 6 problems we have discussed today in the inverse Laplace transform, which is a very important part of Laplace transform, you see that in all the functions you have to modify the function in such a way so that you are in a position to use those 7 standard results that you know. Otherwise it will be very difficult to find out the inverse Laplace transform. So the main part lies in how you remodel the function given to you in such a way so that you are able to find the answer by taking the inverse. And so the main part lies there, how to reduce the function into that form. In every problems of inverse Laplace transform, you will see that this thing will arise. Okay, you won't expect to get any straightforward questions. Okay, you'll be asked, or you may actually, while solving a problem of Laplace or using Laplace transform, you might get some functions which you are not of the known forms, and you have to bring that function into the known form, and that's the way you have to do a lot of problems. So the more the problems you do in this section, the better you become. And with that I come to the end of today's class. I hope I have given you an insight of what is inverse Laplace transform and how to solve a problem of inverse Laplace transform with various techniques. So so that's all for today. So thank you very much for listening to my lecture. So I'll be back in the next lecture with some more properties and theorems of Laplace transform. Thank you very much.